stress tensor, stress vector relationship. Before doing this, let's consider a function phi of xyz. Now, from calculus, differential of phi is equal the partial derivative of phi respect to x dx plus partial phi respect to y dy plus partial derivative of phi respect to z dz. Now, you see, look, I'll draw here the axis. Let's see. We have the x, y, and z, and these are points where function phi is a function of x, y, and z. For instance, suppose phi is a temperature. Temperature is a function of the point. There's a point P over here. So the differential of phi, let's put point P over here. Differential of phi is written right here. Now, P is related to the position vector r. See? So r, let's put r is a function of x, y, and z. You see? So this is x, y, and z. So r, vector r, the position vector r, is a function of the point x, y, and z. This point P is related to the position vector r. Now, dr, using the same procedure, is a partial of partial r respect to x dx plus partial of r respect to y dy plus partial of r respect to z dz. Now, partial of r respect to x, you see this vector r, let's write here, r is equal xi plus yj plus zk. See, look, vector, position vector r, this vector here is xi. This vector over here is yj. You see, if you add xi plus yj, this is a vector xi plus yj. Now, this vector over here plus this vector, you see, is a vector r. You see, look, this vector over here plus this vector, this is a vector zk. You see, this is a vector zk. So, xi plus yj plus zk is a vector r. So, let's write down here, r is equal xi plus yj plus zk is right over there, just right here. Now, what is partial of r with respect to x? You see? Look, I, j, k are constant unit vector. You see, this is I, this is j, this is k. So I, j, k are constant. So the partial derivative of r respect to x is I. Partial derivative r respect to y is j, and partial of r respect to z is k. You see? So dr is I dx plus j dy plus k dz. Let's write right here. You see? Let's write here. Okay, I'll put there. Okay, look. Now, this vector over here, this is I, this is j, and this is k. So dr is equal dxi plus dyj plus dzk. Now, on the other hand, the gradient of a scalar, this is equal to partial of phi respect to xi plus partial phi respect to y j plus partial phi respect to z, the partial derivative, okay, k. You see, look, let's do the dot product. So let's do the dot product of these two vectors. You see, I dot I is 1, I dot j is 0, I dot k is 0. So this will be equal partial derivative with respect to x dx plus partial derivative of phi respect to y dy plus partial derivative with respect to z dz. Now, you look here and you look right here. You see? Now, the gradient of phi dot dr is equal differential of phi. You see? Let's put this relation 1, okay? And this here, relation 2. This is relation 2. So, 1 is equal to, so this is differential of the scalar phi. That's a very important result. Consider now, consider a set of points in which the function phi of x, y, and z is a constant k. The k is constant. Now, let's draw over here. You see this x, y, z, and this is a surface. This we call a surface. You see? Now, any of these points over here has the same value of phi. Okay, surface phi is equal constant. Imagine a temperature, okay? Now, any of these points here has the same temperature. So phi is scalar, is a function of x, y, and z, is equal to constant. Suppose temperature or pressure or any other quantity, physical quantity. Now, look, if a phi is constant, the variation of phi between points, this implies that d phi is equal to 0. You see, because, okay, if I consider the surface phi is equal to constant, and suppose this temperature is 20 degrees, here is 20 degrees, so this is 20 degrees. So the distribution of this point have the same constant phi. Now, the differential phi is equal to 0. Let's plug over here. So this vector here is equal 0. You see, the dot product of this vector with dr will be, let's put here, d phi and is equal 0. Because I'm considering points on the surface. So, this implies that the gradient of phi is perpendicular to dr. You see? Because that's important. Because dr, you see, there's a position vector r. This is dr. Since dr is arbitrary, you see there's many dr over here, you see? So we conclude that nabla phi, let's write down here, you see? Nabla phi is perpendicular to the tangent plane at point P. You see, that's point P here. You see? Because dr is arbitrary, so nabla phi is perpendicular to each of these dr over here, so nabla phi is perpendicular to the plane, the tangent plane at the point P of the surface. If this is a surface, phi is equal constant, so at the point P, you see there's the position vector. That's the point P. Okay, nabla phi is perpendicular to the tangent plane at this point P here. So this is the tangent plane here. See? The tangent plane at point P. Now, only if phi is equal constant. Now, look, d phi is equal 0 is equal partial phi respect to x dx plus partial phi respect to y dy plus partial phi derivative, okay, partial derivative respect to z dz. Look, there is a question here. You see, I used to ask my students, look, if phi is constant, partial derivative of phi respect to x, in general, the student answer, oh, this is 0, this is 0, this is 0, which is not true. Why? Why? You see, partial, what is 0 is differential phi. So this here, in general, these quantities, they are different from 0, see? But the sum of each quantity times the x, this quantity times dy, this quantity times dz, the sum is 0. I'll explain why in the next figure for you to understand. I would like to emphasize that phi is constant only in points of the surface. Now, let's move from point P to point Q. You see, look, when I write from B to Q, you see, this is parallel to this x over here. So this point B does not belong to the surface S. Point A does not belong to the surface S. You see, this is surface S, in which, you see, the only 2 points that belong to surface S is P and Q. Now, look, this is my X3, X. Look, from P to A does not belong to the surface. That's why the partial derivative of phi with respect to x3, let's call z here, I'm sorry, then the x, y, z. Now, the partial derivative of phi with respect to z is different from 0. You see, because A does not belong to the A is not a point of the surface in which phi is constant. You see from here, now, from A to B, A does not belong to S, neither B. So here is a partial of V with respect to Y, because you see this path is parallel to Y, so that's why this is different from 0. The same as this, so BQ or QB is parallel to x-axis. So the partial derivative of phi with respect to x is different from 0. But P and Q, the variation, okay, of phi between P and Q, this will be 0. So delta phi between P and Q, this will be 0, because P and Q belongs to the surface. That's why when you say, okay, phi is a constant, a surface, d phi is 0, but the partial derivatives, they are not necessarily 0, unless if phi is equal constant for any x, y, z, then partial phi respect to x is equal partial phi respect to y is equal partial phi respect to z. This will be 0. And sure, the phi will be 0. Now, only if you have this situation here. You see, because phi is constant, so partial phi for any point in the space. So partial phi respect to x, partial phi respect to y, partial derivative of phi respect to z will be 0. But this is a particular case. We are in this case here on phi is equal a constant, and then I have the surface. That's a very important point. So we learned that number phi is perpendicular to a surface in which phi is constant. That's a very, very important point. Then number phi is perpendicular to the phi is equal k surface. This is a surface. Okay? Now, another second point, okay, these two topics here will be helpful to understand the stress tensor, stress vector relationship. Now, the second one is the equation of the plane. Given three non-collinear points. Now, let's do here x, y, and z. Let's give three non-collinear points. Let's put, for instance, A. I will put numbers, okay? Let's put 1, 0, 1. That's B. Let's put 0, 1, 1. And C. Let's put 1, 1, and 0. Okay? Now the 3 points. Each one, you see, you have the position vector RA. This will be RB, and this is RC. Now, from these 3 points over here, we can construct this vector here, AC and AB. So, let's write down AB, the vector. Do you remember AB will be RB minus RA. This is equal, I'll just put the components over here. You see, RB minus RB minus RA is AB. Do you remember? Look, RA plus AB is equal RB. I want to write here. You see that? One of our first lecture, you see, I wrote that. Let's write here. You see, look, RA plus AB, you see, AB is equal, the resultant here, RB. So, A vector AB is equal RB minus RA. Let's write down over here. Only the components, okay? I'll put here only the components. Look, RB, look, XB is 0 minus 1. So 0 minus 1 is minus 1. Now, 1 minus 0 is 1. And here, 1 minus 1 is 0. So these are the components of the vector AB. Now, let's do the same for AC. AC is equal RC minus RA. You see? Now, this implies, let's write down the components over here. So, RC minus RA, you see, 1 minus 1 is 0. Now, 1 minus 0 is 1. Here, 0 minus 1 is minus 1. Now you can see clearly that there is a plane, okay, that AC and AB lie on this plane. Let's call plane alpha. See? So these 3 points, A, B, and C, they are enough to characterize a plane alpha. You see? Because AC and AB lie in this plane in which I want to know the equation. Now, let's take a point P over here, a generic point P. This point P is X, Y, and Z. Now, what is AP? See, the same. Let's put the blue one here. See, AP. So, AP is equal RP minus RA. This is equal, let's put the component, see, X minus 1. See, X minus 1. Now, Y minus 0. So, Y minus 0. And then Z minus 1. Z minus 1. Z minus 1. Now, let's do as follows. Now, you see, the vector AC, the cross product of vector AC and AB is a vector, let's put here, is a vector here, let's call vector N. You see, by definition, the vector N is AB cross AC. You see? Because from the definition of cross product, N is a vector in which is perpendicular to AB and AC. You see, this is a perpendicular here. You see? Look. Now, it's a vector N. Let's calculate N. N, do you remember, is determinant okay? This is I, J, K. And what are the components of AB? You see, it's minus 1, 1, and 0. What are the components of AC? It will be 0, 0, 1, and minus 1. So let's calculate the determinant here. That's a vector n. See? I'll write down the vector n. Look, now I'll solve this determinant here. Look, if I cross here and here, you see, the determinant will be 1 times minus 1 minus 0. You see, this will be minus I. This is equal minus I. Now, for the J component, you see you cross here and here, you see, here and here. So this will be, in this case, will be, look, minus, minus, you see, because, okay, when I cross J over here, okay, I will do first this one minus this product here. So this product is plus 1, so it will be minus J. Minus J. Now, the last one, you see, will be minus 1 times plus 1 is minus 1. Minus 1 times 0 is 0. So this will be minus 1 minus 1k. So this is a vector n. So n is perpendicular to the plane alpha, see, in which I want to know the equation. So here n is perpendicular because AP belongs to alpha and n is perpendicular to alpha. So n dot AP must be 0 because you see, AP belongs to the plane alpha. N is perpendicular to this plane. So the angle here is 90 degrees. So n dot AP will be 0. Now, this implies, you see, what are the components of n? It's minus 1, minus 1, minus 1. And AP is x minus 1, y minus 0, see? Y minus 0, you see? And z minus 1. So it will be minus 1 times x minus 1. We'll put it here, minus 1 times x minus 1 plus minus 1 times, now y. Let's put y minus 0, see? Now let's put plus and minus, let's put minus here. Now minus 1 times z minus 1. Z minus 1. This will be 0. So here you have, you see, minus x plus 1. Here is minus y. This is minus z plus 1 is equal to 0. So this will be x minus y minus z is equal to minus 2. So x plus y plus z is equal to 2. You see, this is minus, minus, minus. Plus 1 is minus 2. If you multiply by minus 1, that's the equation of the plane. So, given point A, 101, point B, 011, and C, 110, obviously these points are not collinear. So the equation of the plane was a flat surface. It's x plus y plus z is equal to 2. So let's check point A. Point A, x is equal to 1, y is equal to 0, and z is 1. So 1 plus 1 is 2. Now let's check point B. X is 0, y is 1, and z is 1. So 1 plus 1 is 2. Now point C. You see, x is 1, y is 1, and z is 0. 1 plus 1 is 2. You see another point, for instance, let's point P. Could be, for instance, 2 minus 1 plus 1. For instance, see, look, x is equal to, y is minus 1, and z is 1. Minus 1 plus 1 is 0, so x is equal to, for instance, okay? We put the right, look, this is 0. Let's put here minus 1 and 3. You see, look, x is equal to 0, y is minus 1, z is 3. Minus 1 plus 3 is 2. So there are many, many points that belong to the surface. Now we can generalize the equation of the plane just doing this. So any plane in the R3 can be written as, you see, you put ax plus by plus cz is equal to d. You see? And a, b, and c are real numbers, and d also a real number. In our case, a equal b equal c is equal 1, and d was equal 2. Or you could write like this, you see, minus d is equal 0. So this is the equation of the plane, you see, that's the equation of any plane belongs to the space R3. Now, this is important. Now, there is a very important point I would like to show you. This is a surface. So, you see, nabla, look at that. Nabla, I will apply to this function here. You see, this is a function. Look. You could put here is equal to d. This is a function. Look. Phi x, y, z is equal to d, is equal constant. You see? The same we did before. You see, before we did for general case. This is a special case of the flat surface. Let's find the gradient of phi. You see? Gradient of phi is gradient of ax plus by plus cz. You see? The gradient of phi. Now this will be, now here will be right down here, right here. See? Right down here. So this will be gradient of phi is equal partial of phi with respect to x. So this is ai. You see? Now, I'll write here. All right, no problem. Let's write down. This is partial phi respect to xi plus partial phi respect to y j plus partial derivative, okay, with respect to zk. This is equal. Now, let's obtain the derivative of ax plus by plus cz. So the partial derivative will be a, so it will be ai plus partial derivative of phi, this is phi, with respect to y, it will be bj plus partial derivative of phi with respect to z plus ck. Now, you see, if I have a plane, you see, this is x, y, and z. There's a plane. There's a plane. You see? There's a plane. Plane over here. Now, the gradient is perpendicular to any straight line on this plane. And this will be ai plus bj plus ck. You see, that's an important result. So this is a normal. This is a normal to the plane. We can, if you want, we can obtain the unit vector. You see, the unit vector, let's write down n, small n. It will be n divided by the magnitude of n. You see, now n will be gradient of phi by the magnitude of gradient phi. So here you have the unit vector n. So given a plane, A, B, C are the component of the gradient of phi. This is workable only for the plane. If you have another surface, obviously this will be different. See, consider just for you to think for the general case. Suppose I have a sphere, okay, the radius is r, okay, there's a point P, I just wrote this picture here, so this is x, this is y, so this here will be x squared plus y squared. See, this distance here. Let's call OQ. OQ squared. You see, this is a hypotenuse, OQ. Now, this here, this plus this is also a square over here, this perpendicular. So r square will be equal to OQ square plus, let's call this PQ, or let's call S, okay, plus OS square. So OQ square is x square plus y square. OS square is z square. So this is the equation of the sphere. The radius r is constant. Look, this is phi x, y, and z is equal a constant r2. Now let's obtain the gradient of phi. You see, the gradient of phi will be partial phi with respect to x, so this 2xi, plus partial of phi with respect to y, so this is 2yj, plus derivative of phi with respect to zk plus 2zk. You see, phi is variable. It is variable. You see, because for each point you have different vector, gradient vector. So here is a vector. Let's put nabla phi. See, this is a vector nabla phi at point P. In another point right here, you see, you have another vector, nabla phi, at point, let's call P, Q, R, S, let's call T. You see, nabla phi at T is different because it varies x, y, and z. But, if you have a flat surface, like a plane, you see, if you have a plane like this, you're going to use the stress tensor stress vector. You see, if you have a plane like this, see, look, let's see, this is x1, x2, x3. See, we have, for instance, a plane like this. See, look, suppose I have a plane like this. This equation, this plane here, let's write this plane. The equation will be ax1 plus b x2 plus c x3 is equal d. You see, x1, x2, x3 is xyz. Now the gradient, this is phi, okay? Phi of x, y, z. Now you see, here, this particular case, this will be, let's put here x1, x2, x3. This will be E1, E2, the same, okay? This is E3, E3. This will be A, E1, B, E2, and C, E3. E3. Now the gradient of this, will be, look, A, E1 plus B, E2 plus C, E3. This vector here is a constant. So for the plane, the normal, this is a normal, n, is constant. You see, look, there's a normal this plane, and another n, it's parallel, okay? Now, n, you see, there is from there, you see the for there minus n. So all of this vector is a gradient of phi. You see, this is a constant vector because A, B, and C are constant. Just here, the gradient depends on the point. Here, for any point, you have the same normal. See? Let's use this topic on the next lecture, where I'll talk the stress tensor and the stress vector, the relationship.